All right, let's jump right in. Today we're going to take a deep dive into a paper that really shook things up in the machine learning world.
Oh yeah, definitely a game changer.
It's called Attention is All You Need.
Quite a title, huh?
Yeah, pretty bold claim.
Definitely grabs your attention.
It sure does. But when you understand what they're proposing with this transformer model, you might start to think they're onto something.
I mean, the title basically says it all, right? Attention is all you need.
Exactly. So this paper basically says, hey, let's ditch the old way of processing information in neural networks, especially for things like language, and use these things called attention mechanisms instead.
And it was a pretty radical idea at the time,
Yeah, it kind of threw everyone for a loop.
especially folks who were super into recurrent neural networks, RNNs.
Ah, the good old RNN.
It's like those classic examples, LSTMs and GRUs. Those were the workhorses for so long.
Right. For things like language translation, they were the go-to.
Yeah, but RNNs have a bit of a problem, you see.
What's that?
They process information step by step, sequentially.
One word at a time, kind of like reading a sentence?
Exactly. And that can get super slow and clunky, especially when you're dealing with really long sequences of data.
So it's like trying to remember everything you've ever read to understand the last sentence in a book?
Yeah, something like that. It's a lot to keep track of.
I can see how that would be a problem.
And that's where the transformer comes in and basically says, hold on, what if we get rid of this whole sequential processing thing?
Just skip it entirely.
Yep. And instead, we use these attention mechanisms.
Attention mechanisms. Okay.
Yeah. And the idea is to allow the model to focus on the parts of the input that are actually relevant.
Okay, but what does attention even mean in this context? It's like something we do all the time, right?
Exactly. It's like when you're reading a sentence, you're focusing on certain words to understand the meaning.
Or when you're in a noisy room, you can tune out everything else and focus on the person you're talking to.
Exactly. And that's the kind of thing they were going for with this model.
So instead of reading a sentence word by word and trying to remember everything, the transformer can just jump around and focus on what's important.
Yeah, I can kind of skip the boring parts and get right to the good stuff.
That seems way more efficient.
Way more. Now, the way they actually do this, it's with a specific type of attention called scaled dot product attention.
Uh-oh, that sounds complicated.
Don't worry too much about the nitty-gritty details. The main takeaway is that it's a really efficient way for the model to figure out which parts of the input are related to each other.
So they found a way to make the computer pay attention more effectively.
Right, and do it much faster than those old sequential models.
That's impressive. But I'm guessing it's not just one big attention spotlight, right?
Yeah, right. It's not just one, it's actually multiple spotlight.
Multiple spotlights.
Yeah, they use something called multi-head attention.
Multi-head, like it has multiple dot heads.
Exactly. Imagine shining a bunch of different spotlights on different parts of the input all at the same time.
Okay, I can kind of picture that.
Each head focuses on a different aspect of the data, so you can capture a lot more information, a lot more nuance in the relationships between words.
So it's like the model is paying attention to several things at once, kind of like how we do as humans.
Yeah, kind of like that. It can multitask.
Okay, I'm following so far. Now, these multi-head attention layers, how are they actually used in the transformer?
Well, there's actually a few different ways.
Lay it on me.
So first we have encoder-decoder attention. This part involves two main components, the encoder and the decoder.
Encoder-decoder.
Think of it like this. The encoder's job is to process the input sequence.
Okay, so if we're talking about language translation, that would be like the original English sentence.
Exactly. And then the decoder takes that information and uses it to generate the output.
So in our example, that would be the German translation.
You got it. Now, the encoder-decoder attention allows the decoder to look back at the entire input sentence,
The whole thing?
the whole thing, and figure out which parts are most important for generating each word of the translation.
So it's like the decoder is constantly checking in with the encoder, saying, hey, did I get that right?
Exactly. It's like double-checking its work, making sure it's capturing all the nuances of the original sentence.
Pretty clever. So what about this self-attention you mentioned?
Right, so self-attention happens within both the encoder and the decoder.
Within each of them separately.
Exactly. So in the encoder, self-attention lets each word kind of look around and see how it relates to all the other words in the sentence.
It's like each word gets to have a little conversation with all the other words.
Yeah, it's like a little word party in there. And this helps the model understand the overall context and meaning of the sentence.
I can see how that would be useful. But wait, if we're not processing words one by one, don't we lose the order? How do we know which word comes first, second, and so on?
Ah, that's a great question. And it brings us to another really cool part of the transformer. Positional encodings.
Positional encodings. Okay, what are those?
So, since we're not processing words sequentially anymore, we need a way to tell the model where each word sits in the sentence, right?
Right.
Positional encodings are basically like little tags attached to each word.
Tags, okay.
Yeah, they're like little markers that say, hey, I'm the first word, or I'm the third word, and so on.
And how do they create these tags?
They use sine and cosine functions.
Wait, sine and cosine, like from trigonometry class?
Yep, that's the one. You might think it's a little strange to use trigonometry for this, but it turns out these functions are really good at capturing positional information.
So they're using math to tell the computer where the words are supposed to go.
Exactly. It's a really elegant solution. And it means the model can understand word order even without processing the words in a strict sequence.
Wow, so the transformer can capture both the meaning of the words A and D, their order, all thanks to these attention mechanisms and positional encodings.
Exactly. They've managed to solve a lot of problems that were plaguing those older models.
It's starting to feel like this attention is all you need idea might actually have some merit.
The results definitely speak for themselves.
Speaking of results, let's dive into those and see how this thing actually performs. But before we do, I'm still a little fuzzy on this autoregressive property you mentioned earlier.
Oh, right. So the autoregressive property basically means that the decoder generates the output sequence step by step.
Step by step, okay.
It predicts the next word based on the words that have already been generated. Like in our translation example, it would translate the first German word, then use that and the English sentence to translate the second word, and so on.
So it's kind of like writing a story where each word depends on the words that came before it.
Exactly. And the self-attention in the decoder is designed to respect this property, so it only looks at the words that have already been generated.
Okay, that makes sense. Now I'm ready to hear about how the transformer stacks up against the competition. Did it live up to the hype?
Well, oh yeah, it did. The results were pretty mind-blowing.
So tell me, how did it do?
Well, they tested it on a bunch of standard machine translation datasets, the usual benchmarks.
Like English to German, English to French.
Exactly. And guess what?
What?
It crushed it.
Crushed it. Like, really?
Yeah, it achieved state-of-the-art results on all of them.
No way. So not only is it more elegant, it's actually better.
Way better. And get this,
Oh, yeah.
it did all that with significantly less training time.
Wait, so it's faster, too?
Way faster. Compared to those older models, like those massive ensembles of RNNs, the Transformer was like a speed demon.
So it's like showing up to a marathon, finishing first, and then being like, oh, yeah, I only train for half the time.
Haha, exactly. It was a real game changer.
Okay, so the Transformer is this super efficient, super accurate machine translation model.
Right, but the paper didn't just stop there.
Oh, what else did they do?
Well, they wanted to see how tweaking different parts of the model would affect performance, so they experimented with a bunch of variations.
Ooh, I love when researchers do that.
Yeah, it's like they're getting under the hood and tinkering with the engine.
So what kind of things did they try?
One thing they played around with was the number of attention heads.
The heads. So like how many spotlights you're shining on the input.
Exactly. And they found that there's kind of a sweet spot.
Not too many, not too few.
Right, too few heads, and the model can't really capture all the nuances of the relationships between words.
Kind of like trying to understand a complex idea with only a couple of brain cells.
Yeah, something like that. But then if you have too many heads, the model gets bogged down. It becomes too computationally expensive.
So it's all about finding that balance.
Exactly. They also experimented with different sizes for the attention keys.
Attention keys. Remind me what those are again.
Remember how we talked about how the model figures out which parts of the input are related to each other?
Yeah, the scale dot product attention thingy.
Right. Well, the attention keys are basically what determine how strongly those relationships are represented.
So like the bigger the key, the stronger the connection.
Yeah, something like that. And what they found was that larger keys generally led to better performance.
So it's like, if you're trying to express a really complex idea, you need more words, more space to capture all the nuances.
Exactly. You need more room to express yourself.
Okay, that makes sense. So anything else they tinkered with?
Yeah, they also tried using something called dropout during training.
Dropout. What's that?
So dropout is this technique where you randomly drop some of the connections in the neural network.
You just delete them.
Not permanently, just temporarily during training. It's kind of like forcing the model to learn with one hand tied behind its back.
Okay, that sounds counterintuitive. Why would you want to make it harder for the model to learn?
Well, the idea is to prevent the model from memorizing the training data too well.
Memorizing.
Yeah, you don't want the model to just learn the specific examples it sees during training.
You want it to be able to generalize.
Exactly. You want it to be able to handle new, unseen data that it hasn't encountered before.
So dropout is like making sure the model doesn't become a one-trick pony, just good at translating the sentences it's already seen.
Right. It's like teaching it to think on its feet, to adapt to new situations.
Clever. Is there anything else from those variations that really stood out to you?
One thing that I thought was particularly interesting was that even when they removed components like recurrence and convolutions, which were considered essential for sequence processing.
Right, those were the building blocks of the old models.
Exactly. But even without them, the transformer still performed remarkably well.
Wow, so they just ripped out those core components and it still worked.
Yeah, it was like they were saying, see, we told you, attention is all you need.
It's like they're proving their point with every experiment.
Exactly. And it really highlights the power of these attention mechanisms.
You mentioned earlier that they included these visualizations of the attention weights in the paper. Is that what you meant by getting under the hood?
Yeah, these visualizations are super cool. They basically allow you to see what the model is paying attention to as it processes a sentence.
Wait, so you can actually see what parts of the input are lighting up in the model's brain?
Pretty much. It's like you can see which words the model is focusing on as it's trying to understand the meaning.
Okay, now that's something I have to see. Can you give us an example?
Sure. In one of the visualizations, they show the model processing the sentence. The animal didn't cross the street because it was too tired.
Haha, I love that one.
It's a classic. And the interesting thing is that when the model gets to the word it, the attention weights highlight the word animal.
So it's like the model is saying, aha, I know who it refers to. It's the animal.
Exactly. And it figured that out all on its own just by using these attention mechanisms.
Wow, so it's not just translating based on statistical patterns, it's actually understanding the meaning of the sentence.
It really does seem that way.
Incredible. You know, we've talked a lot about how the transformer works. We've seen some of its impressive results, and we've even peeked under the hood a little bit.
And we've seen how this whole attention is all you need idea might actually be more than just edgy title.
Right. But I'm curious, why should our listener care about all this? Is this just about better language translations, or is there something bigger at play here?
That's a great question. And I think
Yeah.
this goes way beyond just language translation.
Really? How so?
Well, if you think about it, this idea that attention is all you need, it could have a huge impact on all sorts of fields.
Like what?
Well, we've talked about language, but what about things like image recognition or music generation?
Yeah, those are hot topics these days.
Exactly. And attention mechanisms are already starting to make waves in those areas too.
How so? I mean, I get how attention works for language, but how do you apply that to images or music?
Well, you can think of any kind of data that has a sequential element.
Sequential, okay.
Like in an image, you have pixels arranged in a certain order, right?
Right.
Yeah. And in music, you have notes and chords played in a sequence.
Right, so you can kind of treat those like sentences in a way.
Exactly. And attention can help the model focus on the most relevant parts of the sequence, whether it's pixels, notes, or something else entirely.
So it's not just about understanding the individual elements, it's about understanding the relationships between them.
Right. And that's where attention really shines.
Oh, wow, this is getting pretty deep.
It is. And it makes you wonder, what other problems could we solve with this approach?
Yeah, that's a good question.
What if we could apply attention to things like financial markets or weather patterns?
Whoa, now you're talking.
Imagine being able to pick out the key factors that drive these complex systems.
That would be incredible.
It would be like having a superpower.
Right, being able to see the patterns that no one else can.
Exactly. And it all comes back to this idea of attention, of focusing on what's truly important.
It's like this fundamental principle that underlies so much of what we do, both as humans and as machines.
I think so. And the more we understand it, the more we can harness its power to solve all sorts of problems.
Well, on that note, I think we've covered a lot of ground today.
We have. We've taken a deep dive into the transformer, explored how it works, looked at some of its impressive results, and even pondered its potential impact on the future.
And I think it's safe to say that attention is all you need is more than just a catchy title.
It's a powerful idea that's changing the way we think about artificial intelligence.
And maybe even intelligence itself.
Who knows what the future holds? But one thing's for sure, attention is going to be a big part of it.
I think you're right about that. Well, that brings us to the end of our deep dive today. We hope you enjoyed it.
And we hope it sparked your curiosity about the power of attention.
Thanks for joining us, and we'll see you next time.